So let's consider a rigid vessel with 10 moles of helium in it. And I should have 10 red dots in there showing those 10 moles of helium. And let's say that this just happens to have a total pressure of, let's just make it easy, 10 atmospheres. Okay, so there's not really an argument that the pressure of the helium, P sub helium, is 10 atmospheres. But if you were to consider what would happen if we added some more gas into this, let's say that we added some blue in here, and let's say that's, let's do 5 of them. We added 5 moles of maybe neon. Well, in this container, if 10 moles of helium exerted 10 atmospheres of pressure, then it would make sense for 5 moles of helium to exert 5 atmospheres of pressure. So we could say that the pressure of the neon then is 5 atmospheres. And we go a little further and we could just say, let's say there's one small green dot in there, and that would be our 1 mole. Let's keep going down the noble gases. Let's say argon. 1 mole of argon. Again, it's logical that if 10 moles of helium exerted 10 atmospheres, 5 moles of neon exerted 5 atmospheres, then 1 mole of argon would exert 1 atmosphere under the same conditions. So again, we could say that the pressure of the argon then is 1 atmosphere. These are the individual pressures being contributed by each of these gases. This 10 atmospheres in red is the pressure just because of the helium. The 5 atmospheres in blue is the pressure just because of the neon. And the 1 atmosphere in green is the pressure just because of the argon. But what if we wanted to know the total pressure of this container? Well, the kinetic molecular theory says if we keep adding more particles in to this container, which was originally at 10 atmospheres, then it's logical that it's going to increase in pressure. And as it turns out, the total pressure of this vessel is nothing more than the sum of the individual pressures of the gases that make it up. So the pressure of the helium plus the pressure of the neon plus the pressure of the argon. So in this case, we're going to find that our total pressure equals 10 plus 5 plus 1, which is 16 atmospheres. The total pressure of this vessel is 16, but these individual components up here, since this is made of different gases, these are called the partial pressures of each of these gases. Out of the total of 16 atmospheres, helium's partial pressure is 10 atmospheres, neon's partial pressure is 5, and argon's partial pressure is 1. So what we've just defined is Dalton's law of partial pressures. And again, the total pressure of any vessel is going to equal the partial pressures of each of the compounds making it up. So let's consider the problem that we have below. A mixture containing 0.765 mole of helium, 0.330 mole of neon, and 0.11 mole of argon is confined in a 10-liter vessel at 25 degrees Celsius. Calculate the partial pressure of each of the gases in the mixture, then find a total pressure. So for each of these, we'll do helium in red. We're given how many moles of helium we have, which is N, 0.765. We know the volume is a 10-liter vessel, and it's at 25 degrees Celsius. That's 298 Kelvin. And we're needing to find the pressure. So PV equals nRT, solving for pressure. Pressure equals nRT divided by the volume. So we'll just plug this in. The pressure of, this is just for helium, is equal to the moles of helium, 0.765, times R, 0.0821, times the Kelvin temperature of 298, all divided by the volume of 10. So when we plug this into our calculator, I'll erase this to save us some space, but when we plug this into the calculator, we find that the pressure of just this helium is equal to 1.87 atmospheres. Okay, so let's repeat. Now that we found the partial pressure of helium, let's find the partial pressure of neon. And again, it's going to be the same setup. P equals nRT over V. In this case, we have 0.33 mole of neon times R, which is 0.0821, times 298, because it's still at 25 degrees Celsius, and it's still in a 10-liter vessel. And you'll find that the pressure due to the neon, the partial pressure of neon, is 0.81 atmospheres. So let's consider something for a second before we go on to argon. Nothing changed in that PV equals nRT equation except for the moles that we plugged in. So we definitely could have said that if 0.765 mole of helium has a pressure of 1.87, we could have set up a proportion to solve this and said, then what will 3.30 mole of neon do? What will be the partial pressure of the neon? And if you cross-multiplied this and found X, you'd have gotten the exact same answer as you got right here. So it's fine to work that either way. If that makes no sense to you, just keep using PV equals nRT. You'll still get the right answer, no problem. So let's go ahead and find the partial pressure due to argon, and I am actually going to carry this one out using the ratios because I think it's a little bit easier. If 0.765 mole of helium exerts a pressure of 1.87, then let's set up a proportion. What will 0.110 mole of argon do? And when you solve for X, we find that the partial pressure of the argon is 0.27 atmospheres. Now let's just make sure these are all logical answers. We have by far the most moles of helium and by far the fewest moles of argon, so it does make sense that our partial pressure of the helium should be significantly larger than the partial pressure of the argon. So we found the partial pressure of each gas. Now in order to find the total pressure, that's just Dalton's law of partial pressures. We're simply going to add them together. The total pressure will equal 1.87 from the helium, plus 0.81 from the neon, plus 0.27 from the argon. Now I got a little lazy in my calculator and I did not carry as many significant digits as I should have, so I got 2.95 atmospheres. If you got a slightly different answer, it's probably because you kept more precision than I did. Now, on a completely unrelated note, two components of gases that you have to understand, two properties rather, are effusion and diffusion. Though they sound similar, they're two very different things, but they're not all that different in some aspects. Effusion is gas escaping through a small hole. For example, the best real-life thing I can do to think of is a helium balloon. When you blow a balloon up with helium, if you come back in a few days, you'll find that that balloon has shrunken dramatically and no longer floats. That's because the helium has effused out of the balloon. Helium is such a small gas particle that it can effuse very readily. So anything escaping from one vessel to another through a small opening is effusion, whereas diffusion is just the spontaneous mixture of two gases. And we tend to think of diffusion as going from high concentration to low concentration. Oop, that's a nice W. But diffusion is typically from high concentration to low concentration, but in all reality, diffusion is simply the mixing of two gases. So there is another law called Graham's law of effusion and diffusion that gives a mathematical formula for the rate of effusion between two particles. You do not have to know this, nor do you have to use it, but you do have to understand the logic behind it. If you were to carry out this proportion where you're comparing the rate of effusion of one gas versus the rate of effusion of another gas, it's actually equal to the square root of the inverses of their molar masses. So what this really means is that larger, and by larger I mean more massive, larger gases effuse and diffuse slower, whereas smaller gases effuse and diffuse more quickly. This makes sense. Gases that are larger assuming they're all at the same temperature, gases that are larger are traveling slower. So it is logical that they're going to effuse or diffuse at a lower rate. So you do not need to know any of this math, but you do need to understand that larger gases effuse and diffuse at a slower rate. And then last, still different but related, is Henry's law. And Henry's law talks about the solubility of gases at given temperatures. So we've got a Dr. Pepper. When you open this Dr. Pepper and you take that first delicious sip, the carbonation is the tingling that you feel in your mouth whenever you drink a soda that's carbonated. Well, if you think about it, a cold soda tends to taste more carbonated than a hot soda. So if we were to think about an open container full of a liquid that has some gases dissolved in it, if these are at a higher temperature, these gas particles will be moving faster, so therefore more of them will be able to escape this liquid. Whereas if you decrease the temperature of this container, fewer of these gas particles would have sufficient energy to escape. So really, all Henry's law is saying that gases tend to be more soluble at lower temperatures. Simply because at lower temperatures, the gases don't have as sufficient of energy to escape. So gases are less soluble at high temperatures, gases are more soluble at low temperatures.